Hello, everybody, and welcome to today's Interest session. Interest is run out of our ETIC, our Entrepreneurship and Technology Innovation Center. That's located in room 107 of Harry Shearer Hall at the Westbury campus, and room 607 and 608 and the Manhattan campus. I'm Dr. Nizik. I'm the director of the ETIC, and I'm also an adjunct associate professor of computer science and cybersecurity at New York Tech. I give these seminars throughout the semesters throughout each year to try to introduce students to technologies that are in high demand in industry, and many of them are proprietary in nature. I mean, they're from a company, so theoretically, you don't always get exposed to them, but their individual companies are hiring for certain things, and they're always in demand. So I give these seminars to make sure that you're aware and understand how to get started on some of these. So today we're talking about designing networks in Packet Tracer. And Packet Tracer is a Cisco product, and Cisco is the #1 producer of networking equipment and routers and switches and firewalls and things like that. And pretty much any organization you go to, you're going to see Cisco equipment. So it's a nice way to get your feet wet without actually really having access to all the equipment at your fingertips. Just to give you an idea where this sits in our lecture series, this is the first lecture for the spring semester. Next week, we're covering creating web applications with C#, so be sure to register for that one as well. Completely different technology set, as far as what we're talking about today, and each one of these sessions is very, very different, but they do introduce you to new technologies and components that you might need to get going career-wise. Yeah, so let's talk about designing networks with Packet Tracer to get started. So when we talk about designing networks, we're talking about computer networking, of course, and that's configuring workstations to servers and tablets to wireless and things like that. So when we talk about that, we're always talking about something called the TCP/IP model, which is what we use today as a standard. There used to be a lot of different models out there, and over the years, as networking became more and more compacted as far as companies that offer networking solutions, we had the OSI model for the longest time, Open Systems Interconnectivity, and that had 7 layers that we still study today in most of our applications, but really today we deal with the TCP/IP model. And that's what everything communicates over. It's a transmission control protocol / internet protocol model. That model is what all networking components and applications use today to send what we know as electronic signals, right? And converting them in some fashion into information that we can recognize and use. The ability to do that means that you have to go from a physical layer, which is simply electrical signals, short and long, basically low and high voltage signals that are converted into zeros and ones. And when we string them together, we have to have a way to move them all the way through an email application, all the way through an SMTP application or something like that. So we have these steps that we go through from taking them from the physical signals that move wirelessly or through electrical signals through wired connections, all the way through the applications which actually use them in a very certain manner, in a very certain organized manner. All right. And what we're talking about today is the design of these things. It's a very practical course, but on this, a very practical session, but on the same note, there's theory behind this that is of great value to organizations. To give you an idea where this lies today, one of the jobs that's out there, the most popular job, is network administrator. And you can see there's just, thousands of jobs that are available in the networking area. And then also you have a very, very lucrative, kind of career path for this. This is a senior administrator, which is about 5 years. If you notice, you see it says 5 years required. Think about that. If you have 2 years already that you get in college working on projects or what have you, and you work in a junior administrator role, which is still a great salary for 3 years, you have 5 years experience. So now you have your senior, you're able to apply for your senior positions. And again, it's an incredibly lucrative and fun career, to be honest with you. I was a network administrator for years, long ago, in the beginning of my career when networking was really all over the place. And it's just fun. You're going all over the place. You're hooking up new sections of network and new nodes to the network, and you're configuring new software that's to work over a network, and it's just a lot of fun. And hopefully today I'll show you kind of how we use tools to simulate that and test network designs. We're talking about connecting equipment in an organization together. When we talk about Wi-Fi, we talk about wireless, we are talking about one small piece of a larger system, right? What seems to be wireless isn't really just wireless. It might be wireless from the device to a particular wireless router, but from that router, it's hardwired. So we're talking about cabling. We're talking about actual cabling in the walls and in your ceilings and all kinds of stuff that's connecting servers and connecting your switches and your clients, your desktop PCs, and so forth. So we're going to learn what each of these are. All right. So this is the domain that we're working. We're actually setting up a local area network in an organization, so that organization can communicate with each other from different offices and stuff. The devices that we talk about and we use in a session like this are just your standard devices. There's switches, they're multi-layer switches, they're modems, they're repeaters, they're bridges, they're routers, they're firewalls. All these different devices are your hardware that makes all of your communications work, right? We connect this hardware through a wire called Ethernet cabling, which we have different categories of. Usually we use category 5E or 6. And basically that cabling looks like this. So we take these devices and we actually wind up connecting these devices with cabling. That cabling is then connected from the device to the wall, from the wall to the classroom, as an example, because we're at New York Tech, and then from the classroom into the computer itself, okay? And those wires come with something called an RJ45 connector, where we're actually connecting these wires into these little ports here. And inside those wires, you actually have 8 wires. It's called twisted pair. There's 4 pairs of twisted wires. The twisting makes the communication move faster with less interference, the actual act of twisting them. And each wire has 2 channels to it to send data. So once you connect these wires together with the RJ45 connector here, that connector then goes into these particular ports and then is able to send data to and from. So it's not like a lamp cord where you have 2, a positive and negative. You have 4 channels of data going back and forth, back and forth, back and forth. And depending on how you wire those, and what type of wiring you select, it's actually controlling the speed of that, right? Is it 10 base T, 10 megabits per second? Is it 100 base T, 100 megabits per second? Is it gigabit per second, right? So the way you wire these copper wires and the way you connect them with each other and the equipment allows you to transmit data faster. Basically, the wires inside get configured with, each one has a solid color and a striped wire that relates to it. And how you wire these into the connector control how data is sent. You can create something called a crossover cable that allows you to connect 2 computers directly together without an intermediate device like a switch. But they have to be wired a certain way. You can configure something to be 10 base T because you don't need that much data to be transferred, and it's a simple, faster type of communication, but it's just not as much data. So you do 10 base T, you can do 100 base T, you can do gigabit, but the wiring changes for how you configure those wires. The other piece is how you configure those wires, but also the device itself has to be able to communicate at higher speeds. A 10 base T switch is only going to run at 10 base T. A 100 base T switch is only going to run at 100 base T. So you have to have the ports and the availability to run at those speeds as well. One of the things that we do to design networks and test them is we use something called Cisco Packet Tracer. Now, Cisco is a Cisco product, Cisco client. I'm sorry, a Cisco manufacturer, and it's Cisco devices. But the methodology here and the framework that you use to design a network in Packet Tracer is identical. It's the same thing you would use for a Fortinet, a router, or any other manufacturer. So working with Cisco Academy and Cisco Packet Tracer is all free, and you get an account and you kind of log in and do what we're going to do today. But on the same note, the things it teaches you about networking and designing a new network, even in a corporate environment using Packet Tracer, allows you to configure that network exactly like you're truly going to configure it in real time, but allows you to test it and all that in a virtual environment, which makes it really attractive. So that's what we're going to do today. And we're going to build local area networks and wireless networks and wide area networks. And we're going to figure out what these different devices are as we do it. Okay, so this is Packet Tracer. It loads just like any other kind of program. It loads with an icon, so you install it. It's an executable, just like any other program you have, and it loads up. But it does some amazing things. It creates a virtual environment for you once it starts, where you're truly working in a network environment. The devices you drop into a Packet Tracer diagram isn't just a diagram tool like Visio that has all kinds of very pretty servers and workstations and switches and stuff, where it looks like a network and it labels the network and you can read it. And it's a great tool and great document. This actually runs as a network in a software environment. It's really very unique. It kind of takes you a second to grasp what's actually happening. But when we design a network diagram in Packet Tracer, it's not just the diagram that you give to somebody, say, hey, go configure this network under this IP addressing scheme and things like that. It's actually a functional networking diagram. Like it actually sends packets back and forth. If you configure it wrong, it won't send it back and forth. You can actually change hardware in these devices. So keep in mind as we do this, the intensity and the importance of the program itself. So let's pretend that we're going to create a fictional organization that has, maybe 3 PCs, a laptop, and a couple of, wireless devices just to keep things simple. And down here, what you'll see these are our network devices. These are our routers and our switches. And then this is our end devices. So we have PCs and laptops and servers and all kinds of fun stuff to connect here, right? This is our cabling. So we have our automatic cabling, which I don't recommend you use because you won't learn as well. But basically we have our console cabling that we use to connect directly to a router or a switch to program it when it first comes out of the box. We have our straight through copper cable, which is what we use almost all the time, connecting our devices to our local area network. We have crossover cables, which we're going to use to connect 2 machines together, but they don't necessarily have a device together. Like let's say you wanted to connect one of your computers home to another computer home directly, but you didn't want to go through your switch. You could use a crossover cable, which is wired differently. We have our fiber cable, we have our phone cable, we have our coaxial cable, which is like your cable modem at home. And finally, we have our serial connections, DTE and DCE. We're going to use DTE in our configurations today. They can connect multiple routers together so that we can connect multiple local area networks together. So a local area network is a series of computers that have something in common. They're in the same room, they're in the same building, or whatever it might be. A wide area network is whenever we separate those networks, they still communicate together, but we separate them either over geographical distance or we separate them out of the local area network connection, right? Which means which really generally means we go through copper connections that are our telephone cables. Essentially, when you look outside and you see the telephone cables, the top one is usually the electricity and the bottom one is usually the fiber and the cable modems connections that we use. So, but we can actually make a network in 2 different locations look like they're on the same network and communicate with each other and share resources, which is kind of an amazing thing. We've been doing it for years, but it's always neat to see it. Right. So let's start with a very basic network. We're going to start with a couple of PCs, and we're going to drop 3 PCs in here. And then we're going to basically put in a laptop over here, and then we're going to put in a server over here. It doesn't really matter. It doesn't really matter where you put them. It's just always fun to pretend that you're really working in an organization. So you want to make it look like you're actually working in an organization. And what does the building look like? This is the front door, and this is where we walk in. We keep our server in the back room, and then the laptop is on, Joe's desk that he comes in part-time, whatever it might be. Okay. So if you see, as we hover over each device, it'll tell us the settings of that device. As I mentioned before, it's not just a diagramming tool. It actually allows you to program these as real systems. So if I were to go into PC1 right now, and I were to configure PC1, I would call it warehouse as an example, right? Under my desktop settings, I can go to a terminal or I can go to a command prompt and I can actually run the operating system on this particular PC. So we're going to call it warehouse, but when I go to my command prompt, I'm actually seeing everything that's on that desktop. So I can actually go and do something called ipconfig and actually get the IP address of that machine like I'm really on it, right? So this isn't just a diagramming tool. It's actually designing what you would be building in a real organization. So it's really, keep that in mind as we go through this piece. It's something that you are really an invaluable tool to understand networking, okay? So let's go to config, and we're going to take this config of this computer right here. We're going to call it warehouse. And then what we're going to do is under the fast Ethernet connection, which is the network card that you plug the RJ45 cable into, we're going to use IPv4, IP version 4. There's IPv version 6 that is a different sizing address, but we're going to use traditional IP version 4, which is 4 octets. Okay. And basically what we wind up doing is we say, let's pick a private networking scheme, which is usually 192.168. Let's choose .10.100. Okay. Now, if you notice 255.255.255.0 pops up, that's called a network mask. Okay. This is a whole lesson in itself, but I will go over it. Each one of these sections is called an octet. 192 is an octet, and it's a 32-bit address. And each octet is 8 bits, right? So it's 8 zeros and ones identifying the number 192.168.10.100. Now, I can't have another 10.100 on my network. I could have a 10.101, a 10.102, but I can't have another 10.100. It's called an IP conflict. And those machines can't communicate together. So what we're going to do is, based on the subnet mask, 255.255.255.0, the first 3 octets are considered the network, and the last one is considered a host. We call it a Class C network or a private network, okay? So the first 3 octets have data in them, and the fourth does not, which means the first 3 octets are your network, the last is your host. Okay, so in this case, the host is numbered 100, but it gives me 1 to 255, so it gives me 255, actually 254 options of devices to put on that network. Now, what if I have more than 254? I've got to go to a Class B network, which we won't get into, but that's basically 255.255.0.0. Okay, so that's a lesson in itself, but you could look into network subnetting and read up on that. But for right now, we're going to call this machine 192.168.10.100. Okay, and we're going to close this out, and then we're going to call, and you notice it changed it to warehouse. Now we're going to go into this one, and we're going to name this one. We're going to go into call this front desk. And we're going to give this an Ethernet address of 192.168, an IP address of 10.101, right? And now we're going to go into this one, and we're going to go to configure, and we're going to call this back office. Okay, and we're going to give this a IP address of 192.168.10.103. Now, because we gave these all Class C addresses on the same network, 192.168.10 dot something, they're all going to be able to communicate together, okay? But they can't communicate now because we haven't created any wiring or any switch for them to communicate through. So what we need to do is we need to go to our networking device, and we're going to basically go to our switches, right? I'm going to drop in a 2960 switch here. And what's going to happen is that I'm going to choose my wiring, and I'm going to choose a straight through copper cable, and I'm going to connect it from my warehouse PC and the fast Ethernet port on its network card. There's a NIC card, NIC, network interface card. And I'm going to drop it from the network card there, and I'm going to drop it into my switch. Now, this is a 24-port switch, so I can choose any one of these ports. Once I communicate with this, drop this port, the switch is recognizing from the machine on its broadcast address what IP address it is and what its MAC address is. MAC address is Media Access Control address. It's the unique address that is burned into the networking card, the communication card at the factory. It's not the PC itself, it's the network card it's using. So this switch is recognizing that this particular MAC address is now on port, whatever we put it into. Okay, and that's going to make it a smart switch, meaning that it's going to know directly where to send information. Now we get a green switch. That's exactly how your switches will behave, by the way. They'll turn, when you plug them in, they'll turn orange, 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 then it'll turn green. That means your wiring is done correctly. That means your communications between the switch and the PC are correct and everything else. And now we're just going to basically go to put in fiber into the fast Ethernet port here and the fast Ethernet port 2 on the switch. And then we're going to connect this PC here to the, now notice port 2 isn't available anymore, port 3 isn't available anymore because I'm using them, right? So it pulls them off of the lists as you go through it. All right, so now these are going to turn green. And once they turn green, I'll be able to send packets through them. Now, what is a packet? A packet is a message that is part of a larger message. If I typed hello world, it would break it up into packets and send it all over the internet, only to come back together at the recipient. And only when the recipient gets all packets from the whole message does it transmit the message. It's a very reliable way of communicating. It was designed back in the 70s called the ARPANET, actually the 60s. But it was the early internet, and basically that same way of sending packets and breaking them up and throwing them and moving them through the network still holds true today, just a lot more advanced. So basically, when I choose this menu up here and I choose this packet, I'm going to choose this particular little envelope here, and I'm going to send a packet from one machine to another machine. And you'll see down here, it says successful. We sent a packet from the warehouse to the front desk successfully. And I can also send a packet from the back office to the front desk. And I can also send a packet from the back office to the warehouse, right? So I have 3 successful packets. So this local area network is now communicating, and it's sending information back and forth. And these machines can share information. They can share printers. They can do whatever they want because they're all connected and talking to each other. But if I simply went into this device and I changed this IP address to 196.8.11.103, because we're using a 24-bit mask, meaning a Class C license, right? 8888. Because we're using this, we're basically now changing the network. So it doesn't see that it's part of the 192.168.10.network anymore. So now what happens is that you won't get any errors. It's still communicating. But when I try to send a packet from one network to the other, I get in progress and I get failed. Okay. So from a network administration perspective, if one machine doesn't connect, all the others are connecting, you want to check your IP address, and you want to basically go back in there into the fast Ethernet and say, I see what I did. I didn't put it on the right network. And once I do that, now when you send packets, now you'll get successful. Okay. So without working on a real hands-on network, this is as close as you're going to get. It is a wonderful, wonderful tool to design networks and test them and function on them. And it lets you increment all your skill sets, kind of as you move through it. Okay, so these 3 machines can share information. But they can't get on the internet, and they can't look at a server and share information off a server. So what we have to do is now we have to go to the server. And we have to go to our, if you notice now our server, we're looking at different hardware and things like that on the server, which is different than the workstation. So it's really, really powerful program to teach you about the different hardware as well. So now if I go into config and I go to my fast Ethernet port here, I have to turn my card on, which is good. It's on already. And my IP address here, it's got to be part of the same network. So I'm going to do 192.168.10. I start at 100. I'm going to make this .5. Okay. I'm going to put, the reason we change numbers and use ranges for equipment is that you always want to know, 1 to 5 are your communication devices, 6 to 20 are your servers, 100 to 200 are your workstations, right? You just, by numbering them properly, you get to know that 5. Oh, if I have an issue with IP5, 192.168.10.5, it's got to be a server because it's in that range, right? So you choose your numbers carefully, your IP addresses carefully to do that. So once we do that, we basically have our physical connection, we have our configuration with the actual IP address. And once that IP address is configured, now I can actually communicate through copper. And I'm going to choose my fast Ethernet port on the server. And I'm going to choose my fast Ethernet 1 port here. It doesn't matter the number of ports you choose on your switch. It doesn't matter. If you choose any one of them, what matters is that what would matter is if you took the cable out and moved it to another one, the switch will have to make adjustments to say that, oh, this server's MAC address is no longer on port 24, it's on port 15 now. Okay, so once this does connect, we'll be able to send packets now to the server as well. And what we do with that is we basically are going to take the packet again. We're now going to send a server. So now our back office computer is going to talk to our server, and we get a successful packet sent as well, which is great. So we're doing things right in this respect. Now, as these get more complex, you want to be able to kind of know what you're looking at. So what you do is you use these little notes, and you basically call this the Chicago network, right? And what we do is we'll put another note here, and we'll call it we'll call the network as 192.168.10.0, right? That is the 10.0 network. So now we can look at this network. Now, when I build another network over here, I won't be confused about it, okay? And you can make as many notes as you want so that you can remember, the server name. So we can name the server. This is the file server 1, right? As you're building these things, you're also going to want to save them from time to time and make sure that you are naming it. So this is interest session 1. So now I can take, they save them as .pkt files. So you can take the PKT file and open it up on any other machine using Packet Tracer. Okay, so now what we want to do is you want to hook a laptop. Now, it is a laptop and it is different device, but laptops usually have also have a hardwired connection into it. So we can basically go from the fast Ethernet port on the switch to the actual fast Ethernet port on the laptop, and then we can configure the laptop to connect. But we have to give the laptop an actual IP address like everything else. Okay, so we're going to give this one 192.168.10. Let's say all laptops are in the 90s, so we give it a .90, right? Just so you know, like 90, 91, 92, they're all laptops. All right, and under the settings here, we can call this, CEO laptop. Okay. For those of you who are unaware why we name things, it's very hard to remember things by MAC address. It's almost impossible. It's very hard to remember things by IP address, more difficult, but by name, and we use something called name resolution, DNS, domain name resolution, and that name resolves to that IP address. So when we ping CEO laptop, we'll get a response just like we would. Now, just so you know, if we're basically sending a packet from the warehouse to the laptop, right, which is 192.168.10.90, we get successful here. But this isn't the real world. This is Packet Tracer. So what it would look like is basically on the device itself, if we go to the desktop and we go to the actual command prompt, we would do an IP config /all to get our IP address. So it's 192.168.10.100, but we know that we want to go to 10.90, right, which is the laptop. And the way we do that, is we use the ping command. So ping sends a packet just like we're doing in Packet Tracer, but directly to the other item. So now we do ping 192.168.10.90. Okay, and if you notice, we're getting replies. Okay, if we sent it to 91, we would not get replies. 91 doesn't exist, right? If we change the IP address on that 90 to 11.90, we wouldn't communicate. So this is a way for devices on the same network using the TCP/IP model and using transmission control protocol / internet protocol to communicate with each other. So TCP/IP can be looked at as a global language that all computers, no matter who manufactures them and when and what operating system, no matter what they do, it's a global language that everyone speaks together when they're leaving their device, right? And that's what you can think about with TCP/IP. Now, what we haven't done is we haven't added in. Give me a second here. We haven't added in. Okay, we haven't added in a router yet, a wireless router, right? So let's put in a wireless router onto our network, and we're going to basically put in, we're going to connect it right to our switch like another device, and we're going to basically connect it to the first switch here. And what we should get is if I connect this to, if I configure this and I configure it to wireless router, okay, and I go to my interface and I go to my LAN interface and I configure this as 192.168.10.200, right? All my wireless routers can be 200 or something like that. Now what happens is that router becomes part of my network as another device. But this device laptop runs Windows and Windows 10 and lets us do a whole bunch of stuff. This file server stores files and shares out files and runs services. These desktops allow you to get just the same thing as a laptop, but not so portable. Each one has their device, it has a specialty, but the wireless router has a very special specialty where it's allowing other wireless devices to connect to this internal network, right? And the way we can see that is if we went to our end devices and we brought in, say, a phone, if we give it a second, that phone should sense the signal of the wireless router and connect. Okay. And if we can test this and see if it works, but if it doesn't, we can configure this phone to be part of this local area network. So it becomes a node just like everything else on the network, but it's communicating wirelessly versus these are communicating through Ethernet, right? Now, the difference between the wiring is this could be gigabit cable and this could be a gigabit network card, this could be a gigabit switch, and you're communicating at a gigabit speed. Wireless is going to be set 802.11 based on what you have, G and N and so forth. Changes, but it's much lower. It's, you know, it's 10 to 100 meg per second versus gigabits per second. So it's great and it's mobile and it's useful, but it's never as much, it's never as fast as your wired networks. Okay. But if we wanted to test this right now, we could send a packet from the laptop to the router just to make sure we're communicating on the network, which is great. But if we wanted to send a packet from the phone to the router, we get in progress and failed. Why is that? Because the phone currently isn't set up to get an IP address automatically, which is called DHCP. At least the router isn't specifically set up to distribute them. So what we want to do is we want to go to wireless, and we're going to go to IP configuration, and we're going to give this an IP address. So we're going to give this 192.168.10.225, right? We can't go over 255, but we can make all wireless devices are in the 225 to 245 range or something like that. And now once this device actually has an IP address that's part of the local area network, now we should be able to communicate with the router, which we can. And now we should be able to communicate with the other devices on the network, which we can. Okay. So, so now we have this Chicago network and it's pretty cool. It's pretty neat. It's a fully configured local area network. All the workstations communicate to a server. A laptop communicates to the workstations and the server. The wireless router gives us access to all of our mobile devices and so forth. And it's a pretty solid design. Okay. Now, what happens when we open up the New York network? Okay, how do we basically say, all right, wait a minute, we're in Chicago, New York. We can't just connect them with an Ethernet. It's 300 feet max. We can't configure that. Even if we used a bunch of bridges, the signal wouldn't be strong enough. So how do we do it? Well, we have to connect one local area network to another. And the way we do that is with a router, not a wireless router like this to allow people access to it. It's with a router that's going to allow us to connect two different routers over long distances together. Okay, and that's what we're going to do now. Okay. Okay, so to make this easier on myself, let me see if I can, well, that's not going to work for me. That's okay. That's okay. Let me see if this will work for me. So I use this, just so you know what I did, I use this select option and then I cut and I pasted it. So now I'm going to call this my New York network. Okay, I've expanded. I bought out my, my competition or whatever it might be. And I'm going to make this a class B. And I'm going to use 10.10. Excuse me. I'm going to make it a class A, and I'm going to make it 10.10. 0.0. Okay. And what this allows us to do is with a class B network is to add, as a class A network, is to add enormous amount of devices on it, because my New York network is, for whatever reason, I'm deciding it's going to grow exponentially compared to the Chicago network. So I'll use a private network addressing scheme 24-bit on the, or class C on the Chicago network. And I'm using a class A, which is always delineated by the 10 dot. It doesn't have to be, but it's just standard. It's nice to use for everyone else. But we're gonna do 255.0.0.0 on that one. Okay. So what we're gonna do is we're gonna take a moment to configure the fact that we're gonna configure this network card here as 10. Actually, I'm going to do, sorry, excuse me, 10.0.0.0. Oh, sorry. 10.10.0.1 and 255.255.0.0.0 is the subnet mask for a class A. And I'm going to do 10.10.0.1 through whatever. I'm just going to make it simple. Okay. So my server is .1. I'm going to now configure my 10.10.0.2. Okay. And do 10.10.0.3. And I'm going to make this 10.10.0.4. And we'll make this 10.10.0.5. We'll make this 10.10.0.6. And we'll make our router 10.10.0.7. Okay. And I'm just going to go back to my server for a second and make sure I configured this right. 10.10.0.1. Yep. Okay. Now, what should happen, I'm just going to save this because we're doing a lot of work we don't want to lose. But what should happen is if I send a packet from my server to my workstation, I get successful. If I send a packet from my workstation to my router, I get successful, right? But we're working on a completely different network now, right? So this is actually 10.0.0.0 because it's a class A, so we're able to use anything in that network and it will still communicate. Okay, now we have two networks and we need this workstation to communicate with this file server and this workstation to communicate with this file server. And we need to set up what we call a wide area network, okay? And both of these networks are extremely functional as is, and they're super productive, but now we have to get them to share data, right? This is a very, very common task and network administrator kind of issue where they say, all right, this year we're connecting the two offices, design a network diagram, test it, evaluate it, right, make it secure, right, which we won't talk about too much in this piece. That's more on the cybersecurity side in another session. But now we have to communicate these two networks. So to do that over longer distances, we have to have a router capable of being able to connect to another router over long distances. Okay. So what we have to do for each network is we have to go into our networking devices, and we have to go to our routers, and we have to pick a router to use. I'm going to use the 2911, and I'm going to put two 2911s in it. Why two? Because each network has to get its own router, and then the routers are actually connected together. Okay. So, and this distance in between here could be thousands of miles, because what we're doing is we're using something called the CSU, DSU to connect to the telephone poles up here. And the telephone poles are carrying the signal to all the different provider locations and then to your building. Okay. We just care about connecting from our building to the router though. All right. So here's how it works. We're basically going to go to our router and we are going to configure our router just like everything else. And we're going to call this the Chicago router. And I'm going to choose my gigabit card here, my internet card. I'm going to turn it on first. They come by default turned off for security purposes, obviously. And I'm going to give this a local area connection on this network, which is 192.168.10.0. So I'm going to call it 192.168.10.1. Okay, that's going to be my actual router ID, network ID on this network. So it's just another device, but all the other devices need to see that. Okay. So when I save that, now I'm going to basically connect it, but instead of connecting it to a 100 megabit port, I'm going to connect it to my gigabit port 0/1. And oh, sorry about that. I didn't mean to do that actually. I'm going to go to excuse me. I'm going to go to my copper straight through, and I'm going to connect from my router, which is my gigabit 00 connector, to my gigabit 1 connector. Okay. And this is going to provide me with gigabit access from the router back to my switch, because it comes capable of doing that. On the same note, I'm going to configure this router, and I'm going to make this router on the other network. Remember, this is the New York router, right? Okay. And on the New York router, on the gigabit card, I'm going to turn that one on. But this one is going to be 10.10.0. Oh, let's say 235, whatever it might be. That's my router. That's my router IP address. And now I'm going to connect that router with the gigabit port 00 to my gigabit port on that switch. And if you want just to make sure, you can always save your changes, as is, and then you can send a packet from, say, your server to your router. Make sure you communicate with it. That's great. And once this connects, we can actually send a packet from say this workstation to this router. It's failing now because it hasn't made the connection yet. The switch is still recognizing the router. Once it turns green, we'll know that. And now we want to send a packet, and we want to send a packet from the PC to the router. Okay, and successful. Now, you always do these tests because as you're troubleshooting something at the more advanced level, if the basic stuff doesn't work, it's incredibly difficult. You just keep making changes and something, banging your head against the wall, but the issue is not on the router, as an example, it's on the network itself. So just make sure those networks are functional and stay functional, and then you can test the next configurations on your router. Now, what you'll see is that even though we have routers now, when we go to send a packet from the warehouse PC to the warehouse 1 PC in New York, it's going to fail. Why? We're connected to our router. Why would it fail? The routers aren't connected. But the routers can't be configured on an Ethernet cable because there's a speed and size and distance limitation to Ethernet, and you can't do it. You've got to connect it to what we call serial cables, which are going to go to the CSU DSU in your building. Then the CSU DSU gets plugged into your telephone cables outside. It's the phone company does it. We just plug into the system. Now, what we have to do is we have to make sure these routers on the physical side actually have a port in the back to plug serial cables in, which we don't. So what we do is we actually turn the power off to this router. This is so much fun when you do this because you don't get to do this on real equipment, but you turn the power off, you'll notice that the connection drops. We're going to drop in an actual serial panel for this so we can turn it on. We're going to turn the router back on. And what you'll see is in the CLI, or the command line interface, this is really truly what you see on Cisco routers. You don't really see all this. This is Cisco Packet Tracer for training. This is actually what you work in. So all the things that you do to a Cisco router from this time on, the interface under CLI is really what you work with and what you see. Okay, so just keep that in mind as you do that. All right, and then basically once we power that up, once we just did that, we just powered that up. That router should come back online. Okay, and we're going to do the same thing to the other one. We're going to go to the router. We're going to go to the settings. I'm sorry, we're going to go to physical, and we're going to turn the router off, and then we're going to drop in a serial cable panel, and then we're going to turn that back on. And once that comes back on, we're going to go to config. You'll see it'll give you an error because it's still booting. But one of the things that I wanted to point out, and the reason is we're getting this red line over here, I forgot to do this. On the actual router settings, if you notice, you have to save it's called flashing the router. So basically you have to save your settings. So on this one, I'm going to choose an IP address of 10.10.0. What do we say, 239 or something like that? So 10.10.0.239, and I'm going to give it a subnet mask of 255.0.0.0. But in my settings, if you notice, I have to save my settings. You don't have to save your workstation or your laptop settings here, but you do have to save the router. And if you look on the command on the CLI interface, this is actually what you'd be typing in on a Cisco router. So if you want to practice real Cisco router commands, you can do that under this program as well. And what it did, though, just so you know, what it did, though, is on this router, it didn't save my changes from before. So what I'm going to do is I'm going to go to config. I'm going to go to my 00 settings here. I'm going to turn the card back on. I'm going to put in 192.168.10. What did I have? Is that 1, right? 10.1. And then I'm going to do settings. Now I'm going to save. Now, if I turn my router back on and off, or if I reload this particular diagram, it'll work. Okay. So now these networks are connected to their router, but the routers aren't connected yet. And what we're going to do is we're going to connect a serial connection between one router, right? Between the serial connection on one router to the serial connection on another. Okay. Now, these particular serial connections represent 1 mile, 10 miles, 600 feet versus 300 feet, or thousands of miles. Okay. There's no distance limitation here because it's going through all the different telephone system. But you will notice these are down because we didn't turn this particular setting on. So here's the way to look at it. Here's one local area network, Chicago network. Here's another local area network, New York network. And then here's another local area network. It's the best way to kind of visualize it. There's 3 local area networks. One is between the routers. One is between all the equipment on network 1. The other is between all the equipment on network 2. So what we're going to do is we're going to go into the Chicago router, and we're going to program the serial 1 interface. We're going to program that to be a clock rate of 128,000. This is how much data is sent over per second, right? So we're going to basically, they just have to be the same. So we're going to turn this on. We're going to give this an IP address, something totally different. We're going to give this an IP address of 192.168.25.1. Right? We're just going to give some totally different so we don't get confused. Okay. So this particular serial connection is like its own network card with its own IP address. And now what we're going to do is we're going to save that, because remember to save. It's very frustrating if you don't save. And now I'm going to go into this router and I'm going to give it on the serial connection, I'm going to give it 128,000 bit per second speed. I'm going to give it 192.168.25. Is that what I said, everybody? 125? I forget, .2. Okay. And I'm going to turn that on. Okay. All right. And now what you'll see is if you go to settings and savings, what you should see, if I did that right, if I think it was 25, but if I did that right, if I send a packet from router 1 to router 2, I get successful. Okay. If I send a packet from my laptop to router 1, I get successful. If I send a laptop from my server to router 1, I get successful. So all the traffic on the network to the router is working, but we'll use these two, laptop and server, just because we know they work. All the traffic on this network is working. The traffic between the routers is working. But if I send a packet from my laptop to the server, it still doesn't work. Why? Because these two routers have no idea, other than that they exist, that each other exists. They have no idea that a whole network lies behind this router and a whole network lies behind this router. They don't know that because we haven't configured what's known as a routing table. Each router has a routing table, and that routing table needs to get updated every time we add new stuff to our network. Okay, so once the communication between the laptop, in this case, and the router are successful, and once the communication between the server and the router on this network, on the New York network, are successful, we now want to be able to have the laptop and the server communicate, but you notice we're getting this kind of in progress and failed. And one of the reasons is that even though all the physical attributes are there for the network and the IP addresses are right, and the network configuration is right, and the routing tables are added, any device on a network needs to know where to get all the routing information. We call it a default gateway. So now that we know that this particular router, if we look at the IP address of this router, on the network is 192.168.10.1. We know that on the laptop, for this test, we want to make the default gateway 192.168.10.1. And on the second router, we know that the IP address is 10.10.0.239. So we want to make the server, in this case, you want to have the default gateway be 10.10.0.239. Okay. And once we set those up, now what you'll see is that the laptop, when it sends a packet to the router, is going to work, but it's also getting all the router information from that. So now when you go to the laptop to the server, now we're getting success, right? So as long as the devices know where to go to get that information, so it knows what's on its network, which is the router IP address usually, then you're good to go. Okay, so that is setting up a local area network with wireless, setting up a second local area network with wireless, connecting those two networks together using routers and serial connections, configuring the routing table on one and the other to point traffic from one network back to its own router, another network back to its own router, and then configuring default gateways on those systems. All right, and once you're done with that, your network design is done and tested and functional, and you can build your real network off of this designed network that you've tested.